We're talking about related rates. These are problems that involve finding the rate of change with respect to time. So everything we've done so far have been respect to which variable? What has been our independent variable pretty much for all the functions? Yeah, x, right? So everything has been done in relation to x. So in the past, maybe we had functions. Let's say I had y is equal to 4x squared plus 6x plus 1. So if we want to find the derivative of this, okay, everything has been done with respect to x. In fact, we can say y becomes 1, and when we attach dy dx, but technically that variable we're finding in relation to x, and same with all these variables. Okay, 8x squared becomes 8x. Technically, we're attaching a dx over dx. And then 6x becomes 6. Technically, we're attaching dx over dx. And the 1 goes to a 0. All right. So every one of our derivative have been dx's. Right? But we also know that anything dx over dx just washes out. So we never saw that played out because it would just always go away. But now we are still finding the derivative, but it's with respect to times. Now, because we're still dealing with x's and y's, all of these variables will remain. So these will become dx over dt, dx over dt, and dy over dt. So we still go through the same process kind of implicitly, but then instead of attaching a d over dt, sorry, d over dx, dy over dx for y variable, we're attaching a d over dt for every x and y variable, or any other variable that shows up. So again, this is an application of implicit differentiation, finding the derivative of variable with respect to time. Okay. Now, let me just run through these steps. These steps are not necessarily in the order that we need to find them. We just have to be able to find each of these over the course of our problem. Okay, so with these are basically kind of word problem forms. So you're always trying to figure out, what are given to you. You want to collect your information. You want to figure out, okay, what am I trying to look for? What's the missing variable that I'm looking for? And this is key here. We're always creating an algebraic or geometric equation. We're always starting off with some foundation, some equation that you know, or equation that they're giving you, and then you're building the derivative equation out of that. So it's always some algebraic or geometric equation that you recognize, and then you're building that slope formula or that rate of change relationship from that equation. But then after you find your equation, you find the derivative, but now it's respect to time, and then you substitute and solve. Now, typically, these problems, the calculus portion is easier. It's the setup that's a little bit more challenging. But pretty much for the most part, your derivative is, I would say, like 90% all power rule, mostly power rule problems. It's the setup that's a bit more challenging. Okay, some important notes here. Remember that when item is getting bigger, your rate is positive. Okay? And if your item is getting smaller, your rate is negative, regardless of direction. I think that's something that some students, we have to kind of get used to. We associate certain directions with signs, right? We associate right with positive and up with positive, left is negative, down is negative, but that's not necessarily the case. Okay, think about what's happening to that rate. If that rate is getting larger or negative, then you're going to be assigning the correct notations. Okay, we'll talk about what that looks like in these examples. So let's do example 1 here. It says the size of a square are increasing at a rate of 5 centimeters per minute. How fast is the area increasing when the sides measure 15 centimeters left? Okay, so let's see here what they're talking about. They mentioned how fast is the area increasing. So let's focus on that word area there. We're looking for how fast the area is changing. What is the area? What geometric shape are we talking about here? Okay. square, right? Square, which, yeah. So let's build that equation first. I'm going to say area is equal to x squared. I'm going to let x represent the side length of one of my squares, or the side length of the square. I like to just go ahead and get the calculus out of the way. That way I can see all the variables that are in play in this problem, and then I can just decide, okay, what information do I have and what information do I not have, or what am I looking for? So we're going to find the derivative of each variable with respect to time. Okay, so power rule can help us get there. And then as soon as we find the derivative, we're going to attach a d over dt for that variable. Okay, what's the derivative of a? Yeah, it's just 1, right? It's like x becomes 1, a becomes 1. But exactly right, we attach dA over dt for that variable, just like how we would with y variables. But instead, before it was dy over dx, now all these problems have this underlying time that's running through it. So everything is with respect to time. Okay, x squared becomes good. But x is no longer the independent variable. We also need to attach a what? Yeah, dx over dt. We're finding the derivative of x with respect to independent variable time, t. Okay, so the nice thing here is now we have everything that we're going to be looking for, right? Or everything that we can potentially gather. Okay. All right, so let's go back to example 1, and I'm going to let's see if we can identify some of these values for variables. It says the sides of a square are increasing at a rate of 5 centimeters per minute. Any idea what this value is referring to? Which of these variables? Yes. Good. So, the hint there is sides of a square. You know that must be x related, but you see these words there: increasing, rate, centimeters per minute. You know it's not going to be a static value. It's going to be a moving value related to x. So anytime you see increasing rates, and the hint also, anything that has a time involvement in your rate, you know it has to be some sort of a d over dt. So in this case, I'm going to say that dx dt is equal to 5. Another key component is looking for those keywords there, increasing. Increasing means that this value is staying positive. So dx dt is a positive 5. Okay, if you see the word decreasing rate, then you will assign that variable with a negative value. Okay, how fast is the area increasing? What are we looking for? Good. Area, we know A is representing area, but you see the word fast and increasing. It must be some sort of a time or rate component. So dA dt is the unknown. When the sides measure 15 centimeters in length. What is that referring to? X, yeah. Okay. A couple of things that's giving that away. You see centimeters, so that is simply as a static value. It's not a moving value. There's no time component here, so x equals 15. So the hard part is just identifying that equation, find the derivative, and then making sure that we know what value is associated with which variable. Okay, so I want to solve for dA dt. I know what dx dt is. I know what x is. I can just plug everything in and find dA dt. So my answer is 150. And for our units, you know okay, so the units is going to match whatever variable you see. Okay. You see there's a numerator denominator portion, so your units will also show that numerator denominator portion. What's the unit for area? Centimeter squared. Okay. So centimeter squared. What's the unit for time? Minutes. Yeah. So you never have to guess or if you're struggling with, wait, what to do with the units, look at your variable. Your variable will tell you exactly how to set units, right? You see that, think of that as your division sign. Find the unit for area, divide it by, and then divide and find the unit for time. So we should just, if you're, some students, they do centimeters per minute squared, right? Hopefully you can catch yourself just by, okay, if I look at that variable, hopefully that variable will kind of clue me in as to what needs to happen. Okay, so this tells us that at this, at the moment when the side length is 15 centimeters, this square is increasing at a rate of 150 square centimeters per minute. Okay, number two, this is one of the first problems that we associate with when it comes to related rates with this triangle problem involving Pythagorean theorem. Okay, so example 2 says 25-foot ladder is leaning against a vertical wall. There's the ladder leaning against the wall, and then the other end is sitting some distance away from the wall on the ground. Okay, 25-foot ladder is leaning against a vertical wall. The bottom of the ladder is being pulled horizontally away from the wall. And that motion is going to cause the top of the ladder to fall as it's getting dragged away. So it's getting pulled horizontally away from the wall at a constant rate of 3 feet per second. How fast is the top of the ladder moving, and what direction when the bottom of the ladder is 15 feet from the wall? So we see first off that the relationship that we can build is that, what is the shape that you see here? Triangle, but more specifically, right triangle. So, and basically we're involving information about the size of the right triangle. So the equation that we have that will relate to the size of a right triangle is Pythagorean theorem. So I'm going to call this x, call this y, and then I'm going to call hypotenuse the c. X squared plus y squared equals z squared. That is the equation that's going to relate to the ever-changing sides of my triangle. Now there's a part that is not changing, but we'll be able to catch that later. Okay, so we know this is our starting equation. So this is our beginning algebraic or geometric equation that relates the variables. Now, I like to just go ahead and find the derivative. It helps me see all the variables in play, and then I can begin to kind of organize what I have and what I don't have. Okay, so every variable gets impacted by time, but we're going to do the derivative of those variables first. And then we'll attach a d over dt for that variable. Okay, so x squared becomes what? 2x. We need to involve something relating to time, because time is what's running through all these problems here. 2x what? Times
dx over dt.
dx over dt, yeah. And you're going to repeat that process and do it for every one of these variables. Okay, so what I like to do is, there's 6 variables here. I'm just going to try to organize my variables. And then kind of one by one, see if what I can do to fill in what I do know. Okay, 25-foot ladder. What is that referring to? C, yeah. Okay. The bottom of the ladder is being pulled horizontally away from the wall at a constant rate of 3 feet per second. D what over dt?
3 dx.
Yeah, good. Dx over dt, right? We're talking about that horizontal motion there, dx over dt. Now, what's happening to the base of this triangle? Increases. Okay. Now, I purposely drew this triangle this way because what direction is it moving? left. What I want you to understand is that the direction has no impact on your signs. Okay. I purposely drew it to left to indicate that, okay, because it's left doesn't mean that it's positive or negative. It's the fact that your length is increasing. That is what's causing your rate to either be positive or negative. If for some reason this length is getting smaller over time, then you want that rate to be a negative. But here, obviously, as the ladder is getting pulled away, the base of this triangle is getting larger, and your rate is going to be positive. Okay, you don't have to put a plus here, but I just want to kind of indicate every time we put down a rate, we have to decide what's happening with that rate. The problem is not going to tell you, oh, make it positive, make it negative. We have to imagine that value over time, what's happening to it. Is it getting larger or is it getting smaller? And that's going to help guide whether you want that rate to be positive or negative.
If it's negative 3 feet per second, it's going to be slammed against the wall.
That's right. So for instance, let's say it's getting pushed against the wall, then that value is getting smaller, then you would want the rate to be a negative. All right, how fast is the top of the ladder moving and in what direction when the bottom of the ladder is 15 feet from the wall? Okay, what are we looking for here? How fast is the top of the ladder moving? dy over dt. That's the unknown. That is our ultimate goal for this part A. When the bottom of the ladder is 15 feet from the wall, what is that referring to? X. Now, if I want to solve for dy dt, I would need all these other variables to be known, right? But I have 3 unknowns, which is causing an issue. But maybe we can kind of just look at it and see if we can fill in these blanks and then find the true unknown, which is at dy dt. Now, y is talking about the height of this triangle at this moment in time. I have x and z. What can I do to solve for y? Yeah, I have an equation that relates it, right? So I can say a squared plus b squared equals c squared, or in this case, x squared plus y squared equals c squared. Now, this is actually going to be a variation of a 3, 4, 5 triangle. So you can solve it using Pythagorean theorem, work it all out, but we can also see that y is going to end up being 20. Right, but technically, it's 15 squared plus y squared equals 25 squared. We subtract 15 squared from both sides, take the square root, and we get y equals 20. Now, dc dt, that's talking about the ladder here. That's talking about the rate of change of the ladder. Is this ladder changing its length over time? No, it's staying 25 the whole time, which means that the rate of change is what? 0. So now that we have everything that we need, we'll insert all the values into our equation, and then we should be able to isolate dy dt. Now, what do you expect out of dy dt at the end? A negative, because it's what? Not because it's going down, decreasing. Yeah, so I don't want us to associate down with negative, because sometimes down could make the value get larger depending on the orientation of the problem. But in this case, we expect y to get smaller, so we know dy dt is going to produce a negative value. Okay, so I know some of these numbers are messy. That zeroes out. That makes it easier. We subtract 90, so 90 divided by 40, or negative 90 divided by 40. Okay, so negative, just like what we suspected. And what's our unit of measure here? Feet per second. Yeah. Or yeah, feet per second. So you see y, right? Okay, so y is it's a one-dimensional unit, and then per second. So look at your derivative, your variable. Your variable will tell you how you're going to set up your units. Okay, hopefully we've saved some room. We need to do part B as well. Part B says, at what rate is the area changing when the bottom ladder is 50 feet from the wall? So the good thing is that we're going to be able to reuse all this information because it's talking about the exact same moment in time. But we're asking, at what rate is the area changing? What area, what shape do you see in front of you? Right triangle. How about the area of a triangle? What's the formula for area of a triangle?
1/2 times the x, 1.
Yeah, 1/2 base times height. We're going to, you can just define with any variable you want. I just decided to choose X, Y, and Z. But if we choose the variable that I built, that I've used, then 1/2 base times height will be 1/2 X times Y. Okay, what do you think we're looking for? What variable are we looking for? The what? The A over dt. Yeah, we're looking for the derivative of area with respect to time. Now, this was pretty easy, right? This A becomes 1 dA dt, but the right side here, if I want to find the derivative, what do I have to involve? Product rule, good. I can't just say, oh, x is dx dt, y is dy dt, and then I'm done. If it was 1/2 x plus 1/2 y, or x plus y, then that's fine. You can do that. But the formula involves multiplication of two variables, and we can't resolve it. We got to go through product rule. Okay, so I'll set it up and see if you guys can build it out. Okay, what's the derivative of what's f prime going to be? One, right, the coefficient, right? 1/2 times
1.
Yes.
dx dt. So x disappears, but remember, time is still impacting every variable. So g will remain as y. Okay, back to f. Okay, 1/2 x. Okay, what's g prime? Dy dt. Right, before it was dy dx with implicit, but now time is the independent variable, so everything is done with respect to time. Okay, we should be able to get everything, pull everything from part A, because we have dx dt, we have y, we have x, dy dt. The reason that we can do this is because it's the exact same moment in time. This is the same moment when the bottom ladder is 15 feet from the wall. What do you think our units of measure will be? Good. Feet squared per second. Look at your variable. Your variable will tell you exactly how to set up your units of measure. Right. I will give you what AP will give you. So College Board will give you volume of sphere, will give you, okay, so basically this, it'll give you pretty much all the formulas except for area of a circle, circumference of a circle, and Pythagorean theorem. Those you have to know. But any other shape, oh, and triangle. Triangle I have to know as well. But any of the three-dimensional shapes, I'll give you. Yeah. So cones, cylinders, spheres, those will be given to you. College Board will give those to you as well. Okay, let's go to page 13. Okay, so this one, I'll give you the formulas. Anybody still need this page? All right, page 2 or page 13, sorry. Example 3, a spherical balloon is being inflated at a rate of 10 cubic centimeters per second. Find the rate of change of the surface area of the balloon at the moment when the surface area is 64 pi. There is volume of a sphere involved and the surface area of a sphere involved. Those formulas will be given to you, and I'll give those to you now. We know volume of a sphere is involved because they're telling us cubic centimeters per second. So anything, we know that cubic centimeter, that's a volume unit there. So we know volume of a sphere is involved in surface area because surface area of a balloon, and we're assuming that this is a spherical balloon here. Okay. So I like to do this. I like to just go ahead and find the derivatives, and that way I can see all the variables and all the equations that's available to me, and then I'm going to list out the information, and then it's going to feel like a puzzle. Like, how am I going to get this information to get here to, okay, so let's start off with, let me write the equation here again. B equals 4/3 r cubed. Now, remember, pi is not a variable. So pi is a number. So there's no need for product rule on the right side. That's just a coefficient. It's going to hang out in front. Power rule is all you need to get to the derivative. Okay, so v becomes what? Derivative? Or well, first v becomes dv over dt. Yep. So, all right. 4/3 pi is going to stay just a number. The derivative is really with the r cubed. R cubed becomes what? And times the r over dt. Yeah, we have two variables in play. Each variable will have a time component associated with it. And just a little bit of cleanup, and then we can come back to it later. Just want to get all the calculus out of the way so that we can just have everything in front of us. Okay, so surface area is 4 pi r squared. Okay, let's find the derivative. S becomes 4 pi is going to stay. It's the r squared that's getting impacted. R squared becomes 2r. Okay, I'm going to gather some information here, but the nice thing here is that everything that we're going to be using to help us solve our problem is going to be in front of us. Okay, so at our disposal, we have the volume equation, we have the surface area equation, and we also have the derivative equations. Just depends on what we need, but those are the tools available here. Okay, let's gather some information here. A spherical balloon is being inflated at a rate of 10 cubic centimeters per second. What variable is that referring to? ev over dt. So if you're ever unsure what variable is talking about, look at the units. The units should help give it away. Cubic centimeters, that's definitely a volume, three-dimensional volume thing, right? Per second, it has to be a time thing. So cubic centimeters, that's dv over dt, right? dv over dt. Now, is that 10 a positive or negative? Remember, anything with rate, you have to manually kind of decide what the sign is going to be. Positive. Okay, why?
Getting bigger.
Bigger, right? Inflated, right? Okay. Okay, let's keep reading the problem here. Find the rate of change at the surface area of the balloon. What are we looking for? ds dt. At the moment when the surface area is 64 pi. Yes. Okay, let's start at the very end, right? Very end, we're just looking for dsdt. But to get to dsdt, we need the r and drdt, which are not explicitly given to us. So we have two pieces of information that we need. So we don't have a direct connection to radius and dr over dt, but we do know dv dt and we know s. How can that surface area help us out? How can this help us find one of the information that we need? Yeah, you have a surface area formula, you put that in, you solve for r, and that's one piece of the puzzle that you need to get to your final variable. And then how can I get to drdt? Is there a path for me to get to drdt to find this information? How can this dv over dt value help me out? Yeah, take that 10, put that in here. I should have already found the r variable using that surface area equation. And then from there, I can get the drdt. And once I get the drdt, then I have the two missing pieces that we need to build out the sdt. Right, so if you can see, you can try those steps. Right, you have everything you need is in front of you. You just have to kind of coordinate how you want to involve the equations in a way that will get you the variables that you need.
Are we going to be allowed to choose a calculator?
Yeah, if the numbers are messy up, you can just copy them this one. Okay, I'll walk through the process, but just at the very end here, our units of measures is ds over dt. What's the unit for surface area? Centimeter squared per second. Yeah. Okay, so just walking through this process, we know that surface area can help us get to the r variable that we need. Take the divide out, take the square root, we get r equals 4. We also have our volume dVdt, which can help us get to the other missing variable that we need, which is drdt. So 10 equals 4 pi r squared. We know 10 is for dVdt. R is 4. Now 16 times 4 is 64. Oh, I do want to point something out here, and this is a common mistake that students make, is it's maybe it's a little bit weird to see that pi in the denominator. We always associate pi as something that's in the numerator, but in this case, this ends up all being divided out in the denominator. So just keep track of your pi. If it ends up in the denominator, then just leave it there, okay? Don't let it just float up to the top because it just feels more comfortable. If algebraically, if that's where pi needs to be, then that's where pi needs to be. So in this case, pi ends up being in the denominator. I can reduce it to 5 over 32 pi. And finally, I'm ready to insert back into the variable I'm looking for here. Replace r with 4. Replace drdt with 5 over 32 pi. The nice thing is a lot of things cancel out because 8 times 4 is 32. And that pi will take out itself between numerator and denominator. We're just left with that 5. And then we talked about the units of measure and how your variable will tell you how to build your units of measure. I'm going to skip number 4. And let's see if we can start. This is the most, this is a cone problem, number 5 here. And cone problems are typically the most algebraically intensive problem. It's not hard, you just have to kind of get used to all the steps required here. So example 5, we have a cone tank, vertex down. So that just means the sharp point is going down here. 10 feet across and 12 feet deep. If water is flowing into the tank at a rate of 10 cubic feet per minute, find the rate of change of the depth of water when the water is 8 feet deep. So one thing that I want to kind of show you about this shape is that there are more variables than we're able to manage. So if you can imagine that there is some water level inside this tank and we see that water is flowing into the tank, so you expect that water to be rising, right? So as it rises, your height is changing and the radius of the cone of this water level is also changing. So we have all these kind of moving parts that we have to keep track of. So what helps is we're going to use this using a similar triangle. So we're going to just look at a side portion of this diagram. So I'm going to redraw this here, and I'm just going to look at just that portion of my cone. I'm going to create a two-dimensional triangular version of that cone. This will give me what information I'm looking for. Now, we also know that the water level inside the tank is also going to take on the shape of a cone. Okay, so I want you guys to imagine this is a cone inside a cone. There's the cone of the container. There's also the cone of the water that's being shaped by the container. Okay. Now, you see that there's a triangle within a triangle, a right triangle within the right triangle here. There is the radius, ever-changing radius of the water level of the cone. That's the inside cone, which is the water level. And then there's also an ever-changing height of the water level inside the cone or inside the container. Now, there's also dimensions associated with the cone. So the dimension here is 10 feet across. Now that's the diameter. What's the radius going to be? 5. And then the height is going to be 12. Now here's the volume equation. The issue is that there are 3 variables, but we can only work out this problem if we get this down to 2 variables. We have too many variables and not enough information. So if I can find a way to find that relationship between radius and height, then I can replace one of the variables. And once it's down to 1 variable, then I can find the derivative and I can go through the same process that I've done before. So here's the relationship that we're going to use to create that connection between radius and height. So we're going to use similar triangles. I can say the radius of the small cone is to the radius of the large cone as the height of the small cone is to the height of the large cone. And we're going to solve for one of the variables. And once we solve for one variable, we can plug in and then we can get the right side down to one variable. So the question is, well, which variable do we solve for? Okay. And the answer is that it doesn't really matter. You can solve for R, you can solve for H, but there's going to be one variable that's going to be a little faster than the other one, because if I can isolate the variable that I'm looking for, then I can get to my answer faster. Now, if you solve for the wrong variable or the slower one, it still works. It just requires one additional step. So I do want to show you that you can get to your answer at the end, even if you end up finding yourself solving for the wrong variable. Okay, I'm going to cross multiply here. Okay, I realize my time's a little short. We will, you guys have homework from your textbook problems. I put it inside your packet. So if you look inside your packet, I have those problems for you here. So there it is, day one problems, and I have all the problems. So you can do it directly inside the packet. But the key is on the website. All right, come up and get your phone. Okay, if you're stuck on the problem like this, I understand, but we'll finish this up tomorrow.
What I plug in, big for H.
Right, that's the thing. They give you the H value, but wait for that. We don't want to lose the variable H. So you're gonna clean everything up, find the derivative first. Once the derivative is there, then you can use that H.
Okay.
Yeah, but don't touch that value. Yeah. Okay.
Do you know how I said ever going to apply for the national map when I said?
Right, so up on my window there, on the other side, there is a QR code. Just take a picture of that QR code, and then you can just go ahead and that's a good from that. There's also a outside my door, you can see that outside. If you have a meeting tomorrow, if you want to, there is something also out there.
I should know how to edit.
Okay, yeah.
And then also Friday, I think.
Okay, yeah, that's right, yeah.
Oh, so that was.
All right, you guys.
That's pretty light. Then, yeah, 5:30. And it's like.
Bro, when did you go to bed?
That's it, yeah, thank you.
Why?
Sweet.
Thank
you. Yeah.
I did so much yesterday. Like, oh yeah, I grinded out 5 surgery. Like, first assignment, which was on Friday. But I was doing
Thank you. All right.
Yes.
Thank you.
No way, actually.
You want to like
When yes. When you like negotiate, you guys can see a roll up the back once it's to. What's a business? No, it's school. That means I'm on this business. Our physics class is like, that's actually.